So, I want to talk about how AI, or neural networks, or artificial intelligence, machine learning, however you want to call it, is actually used in scientific and mathematical research, and the difficulties and stuff. And in some ways, I'm going to discourage it, but in some ways, I'm going to tell you if you're going to use it, how to use it, and the directions that it's headed. So if you're really curious, and the pros and cons, and try to also get rid of the overhype so the useful hype can get through. But first, let's define some terminology and quickly explain how some stuff works. So, what is artificial intelligence? In a broad overview, it's when a computer learns stuff to act smart, or act smarter, or do stuff. Instead of just you write an algorithm and it just does it. So it has some learning component, I would say. Machine learning, I would say the same thing. Now that is not all of that is neural networks actually. That can be taking a bunch of data points and just finding pattern for a bunch of different algorithms, actually. Neural networks are something a bit more specific. And how they work is, think of your brain. There's something called neurons in your brain. There's cells. And each cell is connected to these neurons are connected to other neurons. And how they're connected to each other lets them compute things, and they send signals from one another ones. And sometimes signals turn on neurons, sometimes they turn it off. Well, in a computer, you have transistors and everything that send signals to other transistors, turn them on and off. But that's not what a neuron is in a neural network. A neuron in a neural network is composed of many transistors or something that does something kind of like that. But each of these neurons in your brain has something kind of like an activation function. The activation function is actually more for the artificial neural networks. But what the activation function is you put an input signal. In the case of computers, for the most part, it's a number, just a single number. Now, some more advanced neural networks that we're working on, you put mobile numbers or electrical spike or something like that, or photons or something like that. But let's just say in the simplest case, it's a number. It goes in, and the activation function changes it. Now, the only important thing for the activation function to actually change it is that it has to be non-linear. All you have to know about, for the most part, all you have to really know about what non-linear means in this case is it's not a line. And I'll get to why that's important. If it's a line, then after it goes out of it, it goes into things that have weights. And that's kind of like in a neuron in your brain. First, the signal goes in, it changes, and comes out to hit other neurons. Now, weights just are very simple. They take this output signal that's been transformed by this function that can be anything again that's not a line, and multiplies it by a number. It can be a negative number, it can be a positive number, so it can be -1, it can be 1, it can be a fraction like a half, it can be 25, it can be a big number like 25. Well, some people might not say 25, not a big number, but it's a number. And that's kind of similar to also what happens in your brain, because like some connections are stronger and weaker in your brain. There's positive feedback loops that increase the signal. There's negative feedback loops that decrease one. But not exactly. None of this is exactly like what's happening in your brain. And then it goes into a new neuron that repeats the process. It has an activation function that changes the input, and then goes through some weights as it connects to other ones. And each one connect to 10 different neurons, 100 different neurons, and each of them has different weights in different ways. And the important thing about the weights is when you have a nonlinear function, and you put a nonlinear function in a nonlinear function, sometimes you get an even more complicated nonlinear function. Thing is, when you put a linear function in a linear function, so when you put a line in a line, usually you just get a line out. And if you multiply a line by a number, you still get a line. If you add a number to a line, you still get a line. So weights can also keep a line. If you take a nonlinear function, multiply it by something, and put it into another nonlinear function, you get something more complicated. And each weight, each thing you multiply, if you put that combination, multiply again, and put in something with the weights, it gets more and more complicated. And each weight acts in different ways, in complicated ways. And the reason why, so the more weights and nonlinear stuff, the more complicated your model gets with everything connected, unlike linear things, which actually simplify. And you can try this. If you want to try this, write a linear function, x equals y, for example. Take and multiply it by any number, then take that result and put it into another linear function. And linear functions are forms, if you want in the math, y equals ax plus b. And you can just multiply the output by a number. And if you start working at the math, looking at it, if you keep putting them in stuff, you're always going to get linear functions out. If you try almost any other function that's not a straight line, do the same thing, you're going to get a more fancy one out. And you can also graph this on a computer if you don't want to see it. So that is the basic idea. Now, why do you want to get a more complicated thing for neural networks? Why? Well, the idea is that the more complicated the thing is with all these different weights, the more parameters you can adjust it to fit data. And the idea about fitting data kind of is very interesting, is if you can fit data, you can teach it to learn all these cool behaviors and stuff like that, or do stuff. And in theory, if you have a complex enough function with enough parameters, you can fit any data. Imagine and kind of understand that if you draw a bunch of points on a grid, you can always, and y is your output and x is your input, you can start, if you have a really complicated function, you can go through every single x. And then hit every single y. You can just do all the weird skills. Now, if you want even more, you can add like 3 dimensions, 4 dimensions, 5 dimensions. So you can have as many inputs and stuff as you want. But then you have to figure out the challenge with neural networks though is finding good activation functions, weights, and all those other things. The main challenge is actually training the weights so that the weights actually fit the data or fit how they're doing it. And that leads to training neural networks to do scientific research, which is what I'm going to get into. So all neural networks are just, for the most part, we train them on some data, and they try to match input data with output data. Now, sometimes we do other things to it. I also say that all neural networks, I'm going to get to it, have these weights and activation functions. Some neural networks have more stuff to it. Not all. So, how do we train large language models, and what's the problem with them with research? Well, large language models are trained, so you put in text, you delete, and then it tries to predict what's the next token, they call it, in the text is. But how they're more specifically trained is we delete certain aspects of a word or sentence or sentences, and then it tries to predict, hey, what will come next after you deleted that? So an example of that would be is, my dog is red. But what if I delete the last letter D? I put it into a neural network, and it has to predict the next token. The letter is D. And I train this, but I do this with super large information storage stuff. because I do with so much information, it learns to predict what a correct response is based on previous inputs. And then I might do some fancy stuff with the data to make it better. But this is all about but that can lead to a lot of problems, and especially if your data is not very supervised or good, because there's times like where it gives the wrong date for Passover because it's based on old data, so it looks at the old dates. That's a very common problem with neural networks, is they give outdated data. A lot of times they'll tell you the records are the wrong records or something because they were records from past years ago, or it tells you other information is outdated. Sometimes it also looks up scientific information from science that has still a lot out there but has been recently debunked or retracted papers, or scientific science that's still widely said as science, but we know is wrong, but it's still a lot there out on the internet. Another one that it has done a lot is it does a lot is it just makes up stuff that sounds correct. It also sometimes has thought jokes were real, such as a kind of a little bit inappropriate one is that it said for a while that some AI said cockroaches are called cockroaches because they come out of people's penises. And it turns out that's just from Reddit jokes. So with all this stuff, it's not the most reliable. And also the internet's full of just people saying nonsense. But you might hear about all these researchers using AI to do all sorts of research. So how come that is? Well, typically, what they're actually doing is not large language models, like people think they say. What they're actually doing is models trained on very specific sets of data for the research they're doing. So a good example would be is they have a bunch of data for drug binding, for how much a drug binds to something, a potential drug. We don't know if the drug is good or not, but potential drug, how well it binds to a target, because we want a molecule that binds to a target to trigger a certain response in the body. So you have a bunch of data like that, and you put that in a neural network that trains on that data. It's not this large language model that has a lot of junk that might get in the way. It is good, focused data. Another one, then we can also verify that in the lab. We train a model, we see if the model works well in the lab afterwards. These models can also be more customized and optimized with tricks and stuff for it to be better than that one. Because maybe there is something, maybe we can design better loss functions or architectures. So what a loss function briefly is every time you put in training data in, they try to match to, you put the input data in, and you get output data, and you try to match the outputs of the network to outputs that's coming out while you're still training it. What you do is you have to tell the network how well it did, so it knows what direction that needs to go improve on to update the weights. How well it did, I'm going to talk more about that later, is evaluated by something called a loss function. And it can be as simple as taking something and subtracting the wrong answer from the right answer that it gives. It can be very, very complicated, on the other hand, and sometimes there's multiple loss functions, and we don't always know what the best loss function is. So, another thing we can change is, for a lot of these ones is the architecture more, and the architecture is just how like all the neurons and everything is actually connected. So it's like so there's like different layers oftentimes, and sometimes layers skip stuff and stuff. Is layer 1 connected to layer 2, and then to 3 simply, or is it layer 1 connected to layer 2 and layer 3? Or is it connected, each neuron's connected to 10 ones or 21? Um, it's all very, very complicated, but that's one way. Now, some of these models actually are not that good, just objectively. But you might be wondering, okay, if they're not that good, why would we use it? Well, the reason why is because it's better than anything else when we have so much stuff to sort through at times. So a good example of this is, again, with something with drugs. So oftentimes, when we're looking at drugs and stuff, there is something we use called drug libraries. Now, drug libraries can have millions of potential drugs, anywhere from hundreds to millions of potential drugs. And what we do is we take usually something that we know is kind of like what we want the end drug to look like, but there's a lot of modifications to it that we don't know if it's going to help or hurt the drug. So maybe we have something like a chair. We know the drug needs to look like a chair, but what type of chair? Or something like that. Now, because there's so many possibilities, even a bad model that is maybe better than nothing, just to narrow down the possibilities. Another good example is though, when we have a model that we have something that's incredibly hard to design in the first place, but easy to model actually how well it works. So a good one with that would be like figuring out how strong something is. If you design it's really hard to figure out how to design the strongest structures in certain cases. But a computer sometimes can accurately model how strong the structure is after we design it. So we give it a structure, it designs the structure, then we tell it how good it is. Then it gives us then it says, okay, design the best structure. Then we see if it actually made a good prediction. If not, we say, hey, you messed up. Relearn stuff. The thing with all these things with large language models is they use a lot of computation, they have all these distractions, and they can't really do that kind of thing. Is that, yes, you can sometimes give them feedback back and forth, but not always to the same extent. And not only not to the same extent, it requires you to be more using an expert in the field of like drug binding, structural mechanics, or something like that, and have other models and stuff evaluated, especially if you want to do law feedback, because you might want to do hundreds of iterations back and forth. Now, another one is to solve more complex models with math and stuff that we don't have as good data and clear objectives. Now, when it comes to math and stuff, let's first of all, let's say there's a really difficult math problem out there. Really enormously difficult. When I was starting to hear about AIs solving really complex math, and people were like, okay, and then there's AIs being tested and stuff. So why can't a large language model do it? Well, I recommend you look up videos of large language models playing chess and hilariously making up moves and stuff like that, and see how they're broken. Well, how those models work is they use oftentimes something called reinforcement learning, because we don't have clear data on how to always train them, and the steps. And we also use something called train of thought. So I'm going to tell you how reinforcement learning works with example of chess, and how a model works to solve chess, and why large language models cannot do that. Chess, you might be playing many moves before you win or lose. And if you have two really good chess players that are equally good, it might take forever to win or lose. I mean, if you have one really good player against an awful player, that's a different situation. So, first of all, it's not very clear what pathway we should follow, what move, and there's so many possibilities. Millions to billions of possibilities. So how do we do that? Well, instead we make a guess about something that is probably a good direction. And one way to make it for maybe chess would be to say, hey, come on, let us only plan 10 steps ahead. Let us only look at certain possibilities. Let's look at not 10 possible. Let's say 10 steps ahead, and we're going to play 40 different games where you move in 40 different ways. And out of those games, we're going to choose the 10 that we get the most points according to a system. And the system could be like, okay, I give every chess piece a value. If it has a logarithm, if a chess piece is more valuable, it's a higher number. And I subtract, and if I destroy their piece, I get a number. If they destroy my piece, they subtract a number from me, back and forth. And then I try to steer it to the strategy with the largest number. And then I take the best, and then I train the network. And then I still maybe not won. So then I take that trained one, and I produce several new ideas about what the best strategy is. Or from a different standpoint. Maybe the game has already played a couple rounds, and I train it to figure out, to move in a direction of what I'm going to call my reward function, instead of reward function reinforcement learning is, and I train it again to move in that direction more. And each time I'm training it, I produce a bunch of possibilities, but also choose a pathway to follow to a certain amount. That pathway I choose to follow is because I can't check out all the possibilities. There's too many possibilities. So to train a network to smartly figure out what pathway to follow most likely. If all this sounds complicated, it is. And that's how test playing neural networks actually work, and more advanced ones with playing Go and stuff. And there's also now ones with protein folding, is that they take a bunch of possibilities, try move it in, test them out, figure out which possibilities are the best, and use that to make a decision what more possibilities to check out and see how good they are or bad they are. And then they use that to train network to make better predictions, what they should test out, back and forth. Now, large language models don't have that already built in, and are not specified for that. What you could do is make a wrapper or something like that with the large language models. And how the wrapper would work in a theoretical standpoint is you tell it, hey, play in the chess game 5 steps ahead, or something like that, and plan 5 different move summaries. Then after it tells you, comes up with a plan, you have to come up with something, which one's the best, and which one to work more on, and with more feedback, and it redoes it. And you have to tell it not to do the nonsense. But that's many iterations back and forth, and it's not going to be as good as anything really designed for that. Not nearly as good, not nearly as well, and it's going to use up a lot more computation power, and you might make mistakes, and you have to really think about your reward function in depth. Now, I gave the example with chess, when it comes to math theories, it's really hard to predict. Are you heading in the right direction or not? Are you just saying nonsense or not? I mean, it's really hard to predict when you're doing more basic theoretical work. If something has the objective is, the clear to train this with LLMs. And these are, and for chess playing LLM, for a chess playing neural network, non-LLM or a Go one, they're massive. Really the best ones are massive, and for protein folding. So you have these massive networks that are highly specified, with specialized reward functions that people put in a lot of effort, and these tree searches, they call them, where they're going back and forth and updating. And your thing is not going to reach that level. But what it is going to give you feedback, oftentimes, then, makes you feel good about yourself. And that's going to sound like you're so smart or something like that. And if you're not an expert, it's really hard to tell what sounding just like sounds positive stuff. It's meant to make you feel good, not to actually find the best objective function. So it's going to use all this language, and the more you train it, the more it's going to give you positive feedback that you like, not necessarily the reality. Now, there's also a point that if you're using a large language model to do this stuff, is it really, why hasn't other people thought of it? You have to ask yourself, why haven't other people tried the exact same thing you have tried? Because if I ask you to solve a super hard problem, there's a good chance other people have tried that. And these people are probably going to maybe have a better understanding of what they're saying to a large extent. And if you're not new to the field, it's difficult. So you have all these problems, and people are really working hard on solving them, and neural networks can revolutionize science, but it will have to be very specific trained neural networks for more specific tasks oftentimes. And we always see the fallback of people using neural networks not intelligently. So something now called vibe coding. It's using neural networks to code for you. Now, some of that's okay, but sometimes people use it to code for apps and stuff. It turns out all these apps have major security vulnerabilities, or they have dependencies that are outdated. What I mean is that they work on an old version of a program because that's where the training data was from, or that they just don't work on, they work on one system very well, but not on other systems, or they have flaws in them that are like major bugs and glitches because people thought they were just going to work. They just thought it was going to work, so they didn't test them well enough. And they didn't see all the problems with it. Or they're not optimal code, like a person really understands it. There's sometimes 20 different ways of programming the same function, but some ways might be faster, some ways might be more energy efficient, some ways might be more scalable, and they understand that, but they know that. But the computer doesn't know what you want. It also might just not be as human readable or easy to fix bugs or update when a human writes it. And you get a lot of people that also they've shown that it hurts people's ability to learn programming code. So yes, AI has huge potential in research, but it's probably going to be more for a long time. Certain specific problems where we design AI for those problems specifically, and it's going to be specific types of AI. And if you really want to understand how AI works and all the problems and stuff, before you say you're going to one, I recommend you make an actual neural network yourself. And you might be like, how can I do that? I'm just going to just ChatGPT now online, stuff like that. Well, actually, Python, for example, is free on almost every computer. And Macs and stuff already have installed on some other computers. And there's a bunch of ways, if you tutorials online on YouTube, to make your own first simple neural network in Python. And this will teach you so much more about how they work than you would get from just a lecture or something. And if you really won't trust me so much, you should understand how it works. You also should, for the first time, play with neural networks and try to break them. Try to break ChatGPT in some ways to know its limitation. Any good scientist or mathematician or researcher with math models always tries to figure out the limits of the model and where it breaks to better understand it. So don't always try to make ChatGPT work for you. Try to break it. Okay? Try to find when it doesn't work. And then say, hey, maybe it's not working in these other cases. Then try to also make it more fancy. Once you start with simple neural networks, try to make the more fancy ones with reinforcement learning and all this other stuff. And learn the terminology. Really programming it. Now, reprogramming small models is now super accessible with the hardware and the language and there's many tutorials online and playing around with it. It just takes your time. Now, I also think there's other ways that AI might help, but we have to really be careful and watch it. It might help with citations, formatting, finding papers, stuff like that. But these all have flaws that at some later time I might discuss. There's also a huge energy expenditure and stuff, which I might also discuss at some point. But hopefully you found this interesting. If you have any questions, feel free to comment them. And please really talk to people around you about this, because we're seeing a new boom of what people are calling AI psychosis stuff. And it's scary because these people are going to AI and thinking they're geniuses and stuff, or that this can do stuff for them. And then they stop listening to experts, but also they start self-isolating. And when you confront them, the more down the rabbit hole, the harder it is. So the more they understand beforehand, the less likely they could go to rabbit hole. But also the more understand, the more smart research you might get in AI. So with all this stuff said, please talk to your ones about all the stuff about AI and how it's actually used in scientific research and potentials, and how it's using very specific trained models, not these large language models that spew up stuff. And so examples of large language models saying strawberry wrong, large language models doing ridiculous chess games that have moves that no one should do, large language model messing up, and explain to them that also that if it's so easy to use large language models to solve this stuff, why haven't other people do it? But do that early on, before they're down the rabbit hole. And now, also I encourage people to learn about neural networks because I don't want to just isolate people and learn about stuff on their own through actual research articles and show them how those messes up research articles with outdated stuff. Well, thank you very much for listening. Please like and subscribe. Someday I hope we will get better sound. Bye.